section 5.1, and we're going to talk today about systems of linear equations in two variables. All equations in the form of ax plus by equals c, or y equals mx plus b are straight lines when graphed. Two such equations are called a system of linear equations. A solution to a system of linear equations is an ordered pair that satisfies both equations in the system. For example, 3, 4 satisfies the system right here below. Because this ordered pair, 3 is x and 4 y, 3 plus 4 equals 7, and 3 minus 4 equals negative 1. And I put the 3 and the 4 here, and here, and here. A system of linear equations can have exactly one solution, no solution, or infinitely many solutions. Okay, let's see what we're talking about here. So again, we have equations in the form of this right here, or this. They're just two straight lines, or they're just straight lines on graph. So what can happen is you can graph a line, and you can graph another line, and they could have an ordered pair or one solution. You can also graph a line, and then when you graph the other line, they never cross one another. That would be no solution. That would only happen if the lines are parallel. And then the last case scenario is that you could graph a line, and then when you graph the other line, it's right on top of it. That would be infinitely many solutions. They share every ordered pair. So equations share all solutions or ordered pairs. Okay. So the first thing you do, we're going to determine whether the ordered pairs are solutions. So this is something that we do as a check later on. So let's say I give you the system x plus 2y equals 2 and x minus 2y equals 6. And let's say I give you the ordered pair 4, negative 1. Is this a solution to the system? If it is, this ordered pair has to work in this equation, and it has to satisfy this equation here. And so I have x plus y. So x plus 2y equals 2. And so I do 4 plus 2 times negative 1 equals 2. That's the question there. 4 minus 2 and 2 equals 2. Then I also got to check it into the other equation. So I have x minus 2y equals 6. And so I do 4 minus 2 times negative 1. That equals 6. I get 4 plus 2. And 6 does equal 6. So 4 comma negative 1 is a solution to the system. It has to work in both equations for it to be a solution. Part B, I'm going to check this ordered pair to both equations, negative 4, 3. I get negative 4 plus 6, I get 2 equals 2. And checking the other equation, negative 4 minus 6, I get negative 10, no. So, yes and no. So we have negative 4, 3 is not a solution to the system. has to work in both. It only works in this one, but does not work in that one. So that's that, and this is that. Okay. So let's go ahead and look at the equation for the system in example 1. So we look back at example 1, which is right here. Okay, if we were to actually physically graph this line, and you go back to the intercepts method or do y equals mx plus b, that was something we did in, I believe, chapter 2. If you were to graph those lines, here is the first line, x plus 2y equals 2. And here's the other line, x minus 2y equals 6. And the line represents all the points that are solution to that equation, and so on. 4, -1 is where they intersect, gives the common solution. So this right here, the only point that worked for this equation and worked for that equation. Okay. So on your own, go ahead and consider the following system and determine whether each of these ordered pairs are solutions to the system. And I'm going to go ahead and show your work. Go ahead and pause the video and then check your answer. Okay, so for the first one, when I plugged in 1, 2 into the first system, it worked, and 1, 2 in the second equation system, it worked. So the first one is a yes. The second point, 7, 6, when typed it into or tried it into the first equation, it works. Here it works right here. When I put 7, 6 into the second equation, I got that didn't work. It had to work in both. So if it doesn't work in both, then that is a big bad no. Okay. So let's look at example 1 again, and notice how example 1, the point where they share, or the point of intersection, or the solution they share in common, is nice and pretty, 4, -1. But if you graph two lines randomly, will they always cross at a very nice point? And the answer is no. In fact, probably the majority of the time, the answer is no. So let's go ahead and solve this system by something called the substitution method. In the substitution method, you want to isolate one variable. Then sub value of that variable into the other equation. Okay. So what we're going to do here is I'm going to go ahead and isolate this x. The one that you want to isolate is the one that generally has a coefficient of 1, and the easiest one to get by itself. So if I isolate this x, what I'll do is add 2y both sides. I get x equals 3 plus 2y. First thing I'll do is isolate one variable. That's what I did. I isolated x. Now you want to take the value of that variable, which is this, and you want to plug it into the other equation. Put it right in here for x there. That becomes 5 times 3 plus 2y minus 4y equals 9. Now put this into here. It becomes 5 times all that, and then minus 4y equals 9. And notice how I come up with a new equation. The equation only has y as an unknown. So let's solve this equation. I get 15 plus 10y minus 4y equals 9. So I get 15 plus 6y equals 9. If I subtract 15 from both sides, I get 6y equals -6. If I divide by 6, I get y equals -1. What I just figured there is I figured the ordered pair y value, so this would be the -1. Now I gotta find out what x is. Okay, so to find x, there's no way to do this. You can plug this -1 back into here, here, or even here. That's what I'm gonna do. So x equals 3 plus 2 times -1. So x equals 3 minus 2, x equals 1. So I put the 1 right here. Now I want to check this real quickly, especially since these are nice values. If I plug in 1 here, that would give me 5 times 1, which is 5. It would give me plus 4. It would check into here. I'll do that one mentally. Check in there. If I put 1 in here, it becomes 1. I put -1 in here, it becomes plus 2. So 1 plus 2 is 3. Like that is the right answer. So I always recommend for students to check your order pair back into the system and make sure it works in both. Okay. So on your own, go ahead and solve the system by substitution method, and go ahead and pause the video. And when you get to done, you can check your answer. Okay, so it's all by the substitution method. I get the ordered pair -2, 5. And I went ahead and put this ordered pair back into here. And I got a true statement. It worked in there. When I check this back into here, it also worked. So this is the correct answer. So no, the substitution method is most useful if one of the equations has an isolated variable or one that's easy to isolate. Look at this problem right here. You notice that I'm getting x alone, or you're getting this y alone, getting x alone, or this y alone. If you try to get any of those alone, you're going to end up with fractions. And if that happens, the substitution method is probably not the method that you want to use. So we have something called the addition method, and I call it the addition elimination method. Some book call it the addition method, some book call it the elimination method. I just call it the addition elimination method. I call it both. Okay, let's go back to this equation up here. So what I do is if I add these equations together, if I call it addition method, if I add these terms together, I end up getting 0. There's no more x's. If I add these terms together, I get -2y. If I add these together, I get 4. Now if I divide by -2, I get y equals -2. To find x, I'm going to go ahead and plug this -2 into either one of these y, that one or that one. It does not matter. So I'll put in the first one. So 3x minus 4 times -2 equals 11. I get 3x plus 8 equals 11. Subtract 8 from both sides. I get 3x equals 3. Divide by 3. X equals 1. So that ordered pair, or the solution to the system, is 1, -2. Now, that's nice because if I added these two equations together, one variable eliminated, what I call elimination method, eliminated automatically. That happens sometimes, but not very often. So if I look at this next example 3, if you look at this carefully, if I were to add these two equations together, I would get 12x minus 6y equals 24. Nothing eliminated, and that's not good. You want one of the variables to eliminate immediately. So I'm going to recopy this problem here. 3x plus 2y equals 48, and 9x minus 8y equals -24. So you want to be able to add these and have them eliminate. So what I'm going to do is I'm going to tell you or ask you guys which variable do you want to eliminate. You want to eliminate x or y. It doesn't matter which one you do. Okay. So if I want to eliminate y, I need to have the same number in front of here and one be positive and negative. I'm going to multiply that top equation by 4. And the bottom equation, I'm going to have no change. What happens if I multiply the top equation by 4? That gives me 12x plus 8y equals whatever 48 times 4 is. I get 192. Now the bottom equation I have no change. I get 9x minus 8y equals -24. Notice now that when I add them up, this would eliminate. So now I can add them. So I get 21x equals 192 plus a -24, which give me 168. If I divide both sides by 21, I get x equals 8. To find out now what y is, plug in the 8 into here or here. I get 2y equals 24. I get y equals 12. 8, 12. Okay, so I'm going to check this. If I put 8 and 12 into here, and 8 and 12 into here, you're going to know that both these equations are true. So that would be the answer, solution to the system. Okay, so what I'm going to do is, what I did is I eliminated y, but if I wanted to eliminate x, I would have multiplied the top one by -3, and that would give me -9, and then I would have 9x in the bottom. Okay, on your own, go ahead and do the next problem, and I'll start the next video with the answer to this, and y'all can check answer.